Hi everyone. Today we'll be continuing our foray into the OpenGL programming guide. They're also known as the Red Book here. In the last session we went through the first chapter, which is talking about the introduction to OpenGL. Today we'll be going over the second chapter, which are the shader fundamentals. So in this section we'll be mostly going over all these parts. Yeah, let's get started. So there are a few topics it looks like we'll be covering today. Shaders in OpenGL programmable pipeline on overview of the shading language, interface blocks, compiling shaders, shader subroutines, separate shader objects, and SPIR-V. While I am writing down things and understanding each of these components, I'll also likely take some timing data to make the YouTube's chapter detection algorithm work better. Yeah, so this is the second ever stream in this series, so be sure to check out the first stream before you understand this. Cool. Without further ado, let's get started. So this is around the 116 timeline. Maybe just that for now. Cool. Shaders and OpenGL. The modern OpenGL rendering pipeline relies very heavily on using shaders to process the data. Of course, we've looked at the multiple shaders shading stages here. So we looked at the vertex shader, the tessellation control shader, evaluation shader, geometry shader, and fragment shader. So shaders are used extensively during the OpenGL rendering process. I think it's important to keep in mind that I don't think it was this way throughout the history of OpenGL. At some point, there was fixed pipelines, and where you couldn't really write code for much of these different stages. I don't think the shaders existed. The stages existed as they do right now. So we'll be looking at programmable. We are looking at programmable shader pipelines. So you can write code to configure multiple of these stages here. So shading language is very, very prevalent across all these stages. Back, see, shaders and OpenGL. The modern OpenGL, yeah, it relies very heavily on shaders. Whether for OpenGL are written in a specific language, it's called the GLSL. GLSL is the shading language that we'll be using here. Shading. GL. See. Okay. CPU code is written in C++ or some other CPU programming language. GPU code is written in GLSL. So what we mean by CPU code and GPU code is CPU code is the code that runs on your CPU. GPU code is code that runs on your GPU. The other benefit that we get from writing it in a different language, I guess, is the clear distinction that we can see. I also know that we can share some structures between CPU and GPU. We'll look at that in a little bit more detail. Okay, so this section seems pretty, self-explanatory. It's just saying about the shader language. So now we'll get into the second part of it, which is OpenGL's programmable pipeline. Yeah, in the previous section, we did not look at any of the shaders or code for the shaders at all. We just looked at the high-level rasterization pipeline. Today we'll be looking at these in a little bit more detail. So vertex shading stage receives vertex data. Specify your vertex buffer objects. Okay. We wrote down all the IOs before, so look at chapter 1 if you want to really understand the inputs and outputs for each of these. Yeah, I'm not gonna go into great detail about this. Geometry, shading. Okay, I stuck to this format, but we'll stick to it. Modifies the geometry. Can also discard. Yeah, I think that the author seems to be saying that it's important to consider discards. So we'll note that down. Fragment shading. Fragment shading. Looks at fragments which are interpolated and attaches color. Okay, seems like these are generic programs that can operate on any stages outputs. Okay, cool. So far so good. We still haven't looked at any shader code yet, but we are looking at a sample shader program here. Okay, so the code itself looks like a C code, right? You have semicolons. There's some additional key terms like in, out, like format for this look like some structs that are default. Okay, let's see. Yeah, yeah, like looks like these are the inputs. There are no arguments. These are the outputs again. Okay, yeah, let's look at the shading language in a little bit more detail. Yep, again, GLSL uses GLSL. I think we talked about this earlier as well. We first describe GLSL's requirements and other language constructs that are shared between the various shader stages, and then discuss the features unique to each stage. Okay. Okay, creating shaders with GLSL. The starting point is very simple, it looks like. Very simple code. You specify the version, the main, and that's about it. Looks like there are different some language constructs shared between multiple stages. Some seem to be unique to a specific shading stage. Simple program is very simple. Okay, moving on from there. Declaring the variables. Yep, seems like it's nice. I'm gonna write down some GLSL language characteristics. Here, I think it's gonna be part of this section. So, it's a typed language. Yep. Naming conventions similar to C. Oh, interesting. Types are transparent. Code can assume the data layout types. Okay, which is interesting. Same for C, though based on architecture, we have to kind of do some if-ifs if we want to understand, if you want to like inspect the memory layout of things. It's interesting that we get to do that here as well. Basic. Additional opaque types can also exist. These can be sampler. I don't know what these are yet. Sampler types, image types, atomic counter types. I guess opaque handles are the opposite of transparent, where we can't really look at the underlying layouts or even inspect these in a little bit more detail. Okay, let's look at scoping next. Variables are scoped initialized. Those can be initialized and declared. Support octal, decimal, and hex values. Floats must include a decimal point. Seems to make sense. So far, things seem to make sense so far. No implicit type conversions like C++. It needs to explicitly call figure. Okay. Okay, seems reasonable so far. I guess like we'll pick some of these up while going through the code, but it's good to have this thing as well. Aggregate types. Yeah. Okay, so there's some vector and matrix types. That's fine. You know, aggregate types, access, vec for, mat for, etc. Sure. Okay. Oh, this is interesting. So when you're accessing things, it looks like you can access through XYZW, RGBA, or STPQ for positions, color, and texture coordinates. Okay, I don't think we know from just looking at a vector whether it's one of the other or not. So we can see. Oh, so things can repeat as well. So color.rrr creates a new vector with 3 elements. Interesting language. I don't think I've seen any language like this before, but it's good to know. This seems very new to me, so I'm gonna write this down somewhere. Accessing element. Interesting. Done through index or component accessor. Okay, so let's look at some examples here. Let's say we have vec3 color equals vec3 of make a vec for RGBA, right? 0. I think this is a floating vector, so we'll just keep things as floats. 8.0, 2.0, and alpha value of 0.8. Okay. Valid accessor thirds illuminance color. There's a famous Indian movie called RRR, so this reminds me of that. You can also do things like vec3 other equals at abgr. You can also do color equals that's the example, that's the book, so you can just keep it like that. Vec4 color is okay. Let's leave it like so. Valid. Even the comment was invalid, so okay. I think this drives things down my brain pretty well, so we'll go. Structures, there are structs. Okay. Language support for structures as well. Gloat. Classic name for variable that's gloating over its lifetime. Precision. Okay, sure. For example, makes things clear. Get this. Also supports array types. I'm just gonna use this example. You can also have I'm gonna use C-style array names. Okay. Storage qualifiers. Interesting. Language seems pretty mature to me. Const in out uniform buffer shared. Yeah, so const is read only. In it seems like the input argument for the shader out seems like an output from the current shader uniform. is a value passed to the shader from the application. It's constant across a given primitive. I think we'll know more about this later. Buffer specifies read write memory shared with the application. I guess shared storage buffer, shared storage buffer. It's shared with CPU and GPU. Looks like shared is the variables are shared in a local work group. I don't know what a work group is. We'll figure it out. Excuse me. So there seems to be quite a bit of section about uniforms, but we'll know about this as we do things. Oh, they support operator overloading as well. I don't know if they're allowed defining it or not. This is descriptive. If else switch and loops. Yeah, break continue return seem pretty self-explanatory. Discard seems to be the only new one for us to think about here. Okay. Functions permit you to reuse code. Makes sense. Yeah, pretty standard parameter qualifiers for functions. Computational invariance. I see. Okay, so there's this notion of computational invariance. I don't think these are, apparently these do exist in CPU applications as well, but we don't really talk about them in great detail. Looks like this is a feature that's kind of interesting to look at. So I'm gonna create a subsection for this additional invariance. Computations done twice result in difference of results. Okay, there are, this might be a problem to multi-pass algorithms due to variance. I guess the invariant and precise qualifiers exist to avoid this behavior. Variant can be applied to output variables to guarantee precision. As the standard GL invariant can be useful to mark all to impose invariance on all variables in a shader. Just for this. Is similar to invariant, but be applied to any computed variable or return value. Imposes guarantees reproducibility. I guess one thing that's time penalty. Yeah. There's also a shader preprocessor. Yeah, if defs. Preprocessor conditionals, solve good. Pragma is compiler control. Optimization, compiler optimization. Okay. Debug on, debug off. Okay. Okay, so just at a high level, right? There's preprocessors, conditionals, and compiler control. These are all pretty similar to C. I'm not going to write this down. You can write a note about extensions because I think these are unique extensions. Vendor. Let me just write this down over here. Can enhance OpenGL. Vendors may choose to include these. Yeah, as such, they're not uniform across all platform implementations, I bet. There are directives like Okay. Okay, cool. So far, so good. Let's look at interface blocks. Shader variables shared with the application or between stages can be sometimes must be organized into blocks of variables. Uniform variables can be organized into uniform blocks, input and output variables into in and out blocks, shared storage buffers into buffer blocks. These all have similar form. First, we use uniform demonstrate showing first in anonymous form. Okay, uniform B is vec4. Okay, okay. Okay, so they're just grouping things of the similar nature. You can even control the layout of the interface block, it looks like. You can do shared, row major, column major. When you share a buffer between sharers in the application, both need to agree on what memory layout and offsets are holding these members, as explicit layout is needed. That is what STD40 and STD430 provide. Okay. I think as long as we share the structs between shaders, we can do things. Like we can avoid the problem of having differing layouts, but we'll see. Okay. Hmm. We have some function calls to deal with uniforms as well. All right. So let's look at an example. I think that'll, you know, make things a lot clearer for us. So I'm gonna use this example verbatim over here. Is there a way to remove this thing? How with it? Let's go. Okay, so let's look at this, right? So it says that we're using OpenGL version 4.4.0. The layout is conforming to this standard for this uniform interface block. We have float size starts at byte 0, starts at byte 32. Okay, starts at align 1024. Next multiple of 1024. Okay, assigned next offset after 812. Okay, so all sounds good. I don't know why you'd want to use this as opposed to just using regular struct format, but we'll see. Find offsets and various uniform variables inside the named uniform blocks in your shader. Once you know the location of these variables, instantiate the data just as you would. So it seems like we have to be very careful about blocks are useful to share information between app shaders. Important to be aware of the data layouts. Okay, so accessing uniform blocks from your application, because uniform variables form a bridge to share data between sharers in the application, you need to find offsets of various uniform variables inside the named uniform blocks in your sharers. Once you know the location of these variables, you can initialize them with data just as you would any type of buffer object. Okay, let's assume that you know the names of the uniform blocks used inside the sharers of your application. The first step is initializing the uniform variables in your uniform block is to obtain the index of the block of a given program. Get uniform block index returns an essential piece of information required to complete the mapping of uniform variables into your sharers, to your application server space. I think we'll look at this when we get to this. And we got to it. Okay, so let's look at the sharer code here. Standard, uniforms, position, color. So the uniform block is called uniforms. We have fragment shader, and we have the main block. So initialize the values in the uniform block index, program, and uniforms. Okay, so the block, get active uniform block IV to be your size, buffer is malloc. Okay, so we got the buffer here. Installation, scale, rotation enabled, uniforms. So if we look at the uniform, right, it has translation, scale, rotation, and enabled. Translation, scale, rotation, and enabled, they're all in CPU land so far. So you are specifically declaring the names that we are using: translation, scale, rotation, enabled. Indices, size, offset, and type. So we're getting the size, offset, and type. And for each of these, we'll probably use the index of that somewhere. Yeah, we're using enum, so we'll get the indices to the right places. Time buffer, yeah, same makes sense. Okay, buffer UVS size. Wow, this is super descriptive. Buffer blocks. Hopefully they follow the same convention as uniform blocks. A lot of boilerplate, but I guess that's needed. In-out blocks, out blocks. Compiling shares. Okay, so this is all pretty standard. There's definitely ways in which you have to bind things. We'll look at that in a little bit more detail when we start looking at more applications. But let's look at compiling shaders for now. We are minute, say 40. Okay. Shader compilation pipeline is as follows. So we create a shader object. We compile the source into the object, verify the compilation is successful. Okay. And I'm gonna call this step 1. No. All right, this looks better. I'm gonna call this compilation. Looking. Create a shader program different from. I don't know why this has to be so complex. Attach shader objects to the shader program. Link the shader program. Verify link success. Use profit. Just gonna call this profit. Okay. We'll be looking at each of these in great detail. So create shader, shader source, compile shader, get shader info log, create program. We'll talk about shader sources. Shader sources can be reused across shader programs. This is improve compilation times. Okay, linking. Okay, first three steps seem very simple. Create program, link program, delete shader, use program. Okay. Okay. So let's get into shader subroutines now. JS allows you to define functions and shaders. The call flow of these functions was always static. To dynamically select between multiple functions, you can either create two distinct shaders or use an if statement to make a runtime selection. Okay. Similar to function pointers, you can switch calls on if or pass the right function pointer. are meant to be, these are shader subroutines are meant to be keyword and will be good. Will be good. I think an example here is very useful. It's a little complex topic, I feel. So let's say you have a subroutine which returns a vector 4, call it light funk, which takes a vector 3. This takes vector 3, returns vector 4. Okay, so let's say we have multiple implementations of the light funk in light funk. Let's call one of them as ambient lighting. Ambient takes in a vector 3 of n and return preals.ambient. Let's say over here we have views. We call this diffuse times max of dot of lies and whatever, right? Don't really care here. And we have a subroutine uniform funk material shader, right? This uniform can be set in the CPU code be either ambient or diffuse. This letting us control the light funk dynamically. This looks good. LGTM. Let's go. How do I go back? This is painful. Okay. Okay. Yep, I think we're good. We are go. Wow. Share supporting separate share objects. Did I miss a section? Did I miss a section? Okay. Yep. Yep, I did miss section. So you're almost the 50th minute. Cool. Prior to OpenGL 3.1, only a single shader program could be bound at any one time in an application's execution. This was inconvenient if your application used multiple fragment shaders for a collection of geometry that was transformed using the same vertex shader. Okay, this caused you to need to have multiple programs around that duplicate the same vertex shader, wasting resources on duplicating code. Separate shader programs allow shader stages from various programs to be combined into the program pipeline. Okay, separate shader objects. Shader stages from various programs to be used to combine into a program pipeline. Okay. In earlier versions, the single shader program can be bound at one time. Inconvenient. Have used multiple frag shaders all used same vertex shader. Let's spend a second to understand this. If so we can only have a single shader program that's bound at one time. So each shader program can have multiple shader shader objects. Okay. Hmm. So one program cannot have multiple vertex shaders. That makes sense. So let's say we have multiple fragment shaders. Same argument goes to fragment shaders. So one program cannot have multiple fragment shaders. Okay. Let's read a little bit further. The first step is to create a shader program that's usable in the shader pipeline. Then by calling get program parameter I. Yeah, I'm not getting this very well. I think I need to like a little bit more about this. Doesn't make sense to me. I'm gonna pause for a second and then resume. Okay, after some Googling, I found this link about the specification that adds separate shader objects. So I think let's go through this and see if it gives us any more clarity. So conventional GLSL requires multiple shader stages. I'm gonna add this as a reference. Redbook. Uh, let's just copy the title over here. So yeah, the single monolithic program object to specify shader for each stage. While GLSL's monolithic approach has some advantages for optimizing shaders as a unit that can span multiple stages, all existing GPU hardware support more flexible mix and match. Shaders written for HLSL9, CG, the prior OpenGL assembly, and game consoles favor more mix and match approach. Okay, so looks like you can get components out of, so instead of linking, let me just write the notes from mental model here. instead of linking all the shader sources to a monolith program, you can have, see, can have a program pipeline object. Okay, so instead of changing things to the active shader program, it looks like this allows changing shaders to arbitrary program bound to the pipeline. I'm using terms here that I'm not very familiar with, but I'm hoping that we'll know more about this. With this knowledge, let's read this again. So we can bind multiple shader programs through pipelines, is what I'm understanding, and you can change things for any of the things that are. Okay. Okay, so you can get things for each program. So this seems like an advanced concept, but in reality, it just feels like you can just access multiple programs at any time, and you can link multiple components each of them. Okay, let's get to SPIR-V. SPIR-V 59. The pronoun standard intermediate language that provides an alternative for distributing shaders. Alternative way of distributing shaders. Typically, we have GLSL sources, and then GLSL sources we can SPIR-V output, also known as generated SPIR-V. Each SPIR-V module, SPIR-V is created, distributed, and consumed. It's called modules. A SPIR-V module can live in memory as 32-bit words and can be stored in a file again. This is a serializable format of 32-bit words. And reside in memory or disk. So each SPIR-V module contains one or more entry points as a place to begin shader execution, and each entry point knows what OpenGL pipeline stage it belongs to. Okay. SPIR-V modules. Contain multiple entry points. Each entry point knows what OpenGL pipeline stage it belongs to. Each entry point must form a single complete OpenGL pipeline stage. I want to see if they talk about pipelines anywhere before. Once your collection of shared programs is combined, you need to use the new shared pipeline constructs. Okay. I think shared pipeline is collection of shader programs are linked. Multiple pipelines can exist as of separate shaders being allowed. Okay. As with most GL pipeline objects, there is a gen bind delete sequence to make. Shader pipeline is called by a create bound program pipeline, which will create an unused program pipeline identifier, bind pipeline, delete program pipeline, use program stages, program objects that have been marked as separable to the pipeline. So pipeline is this whole structure of multiple fragment shaders, multiple shaders, sorry. Each of these can be filled. Okay, so now we know what pipelines. Okay. These are fully linked programs are done by a front-end compiler using other from a lang such as GLSL. Makes sense. Specialized meaning changing the values specially identified constants inside the module before final compilation runtime. Yeah, I don't think that's too necessary for us. We'll figure that out later. Reasons to choose SPIR-V. Better portability. This is an interesting section to have. We too vague. Platform impulse change widely. Okay. language choices. We have more than use GLSL or metal or other. Right, that's nice. Smaller size. Obfuscation. GLSL needs to be sources distributed. Okay. Okay, so there's functions to use SPIR-V, share binary, specialized share. So I'm guessing that there are ways in which we can generate SPIR-V. Given that we're not gonna be looking at these in great detail right now, I'm gonna skip this section until we write actual code that lets us test all of these things. Yeah. Okay, subroutines are not supported in SPIR-V. Okay, let's see. Using GLSL to generate SPIR-V for OpenGL. Okay, this section I think is pretty clear to me that we need some kind of a compiler. I'm gonna look at this later. So there is concept of specialization. Specialization constants can greatly reduce the number of variants of shaders to distribute. They allow late changing of a shader constant without having to manually generate a new shader. So there's this thing called layout constant ID, it looks like. So you can specialize shader and probably pass a value and you can do it. So there's some deprecated things that are present. Looks like you can remove them. Makes sense. Changes to GLSL for SPIR-V generation. Okay, so there are a few functions that change between these or not compatible with SPIR-V. So we might have to use newer ones, which I think is okay. We can think about this when we run into them. Hopefully, the shader compiler will give us valid errors so that we can replace them with proper compatible GL calls. What's instead SPIR-V? Interesting. SPIR-V is a simple, pure binary form representing a high-level intermediate language. It stores this form as linear sequence of 32-bit words. When you get a result from an offline compiler or set it into API, it will be such a stream of 32-bit words, but you have to multiply by 4 to get the byte count expected by shared binary. Okay. SPIR-V loses very little information from shared written in high-level language. Can retain nested control and other high-level constructs. Type natives to GLSL and decoration. So SPIR-V is more general than just GLSL. Okay. Simple binary form contains superset, not a strict superset, contains there loses very little information during run and compilation. I'm excited to honestly try out SPIR-V on some GLSL series if we write out and see how it works. Okay, looks like that ends chapter 2 for us. Thank you all for working through this with me. I know it's a lot. As usual, I will try to put everything in the description. Please let me know if you want me to go a little bit more in detail about some specific thing, or change anything about the videos. Thank you. Have a nice day.